So welcome to the presentation 12 of this series of presentations on algebraic structures. So what we want to do is we would like to continue with our discussion of isomorphisms between two groups, and what we are working under, an assumption, and it's a continuation from the previous presentation where we did isomorphism, that G1 is isomorphic to G2. Okay, and just a very quick refresh, what we mean by that is that there is an isomorphism between G1 and G2, uh, you know, which respects, that is a 1-1 onto map that respects the operations between the two. So what we have to do is that we have to show if G1 has a subgroup of order n, then G2 also has a subgroup of order n. So what we would do is that first we will let that, or let's let H be a subgroup of order n in G1. Okay. So first what we would do is that we shall show that its image, that is f of H, is, or rather phi of H, okay, is a subgroup of, or rather first just a subgroup of G2. Okay, so this is what we are going to look at first, and so is a subgroup of G2, and then we shall take the older part. All right, so let's just write that as our claim. So if we are claiming that this is a subgroup in G2, what we must show is this. Remember this, G2 is a group and this is a subset. So this has fewer requirements to show. And all that we have to show is this, that if X and Y, they are in phi H, okay, then what should that imply? That should imply that XY inverse should also be in phi H. Okay, so XY inverse is in phi H. Okay, so if X and Y are in phi H, right, what does that imply? That, remember this is, I mean, of course, here H to phi H is an onto map. So that means we can find, or there exist, okay, let's just say there exist. I like that better. There exist A and B in H, because we are looking at direct image of H, right? Such that what? Such that fx is, or rather fa is x, right? Fa is x and f of b is y. Okay, so and this is because of the property that phi of h is the image of h. So let's just look at that. So all that we are trying to say is that we have G1, G2, and here we have H, a subgroup, and here we have phi H, another subgroup. And we got an isomorphism phi between those two. So what we wanted to show was that if X and Y, they are in phi of H, okay, then I have to show that XY inverse is also in phi of H. So again, since this is direct image, we have a pre-image of X, A in here, right? Okay, and then pre-image of Y, B in here. Now, H is a subgroup, so what will that do? That will give us AB inverse in H, right? So we have that AB inverse belongs to H, and what will that do then is that phi of AB inverse that belongs to phi of H, right? Now, who is phi AB inverse? Phi AB inverse, remember, we can write O1, O2, but let's just keep that as understood, that here our operation is O1 and now the operation is O2. So we got phi A times phi B inverse, and which is going to be what? Which is going to be simply phi A is who? X, right? And well, let's use the property that inverse is carried to the corresponding inverse. So this becomes phi B inverse. So this will, phi B is who? Y. So this becomes X Y inverse, right? Okay. And then since this is in f of phi of H, right? So therefore this is going to be in phi of H, all right? So, so if X and Y are in phi of H, so is XY inverse, all right? And then phi of H is going to be a subgroup of G2, okay? So we just showed on our blackboard that phi H is a subgroup of G2. Now, remember this, that by the part 2 of this theorem that we just did, and this theorem we are doing from our book, The Abstract Algebra and Application by Judson. According to that, these two would have the same order, right? And uh, what that means is if H has order n, then phi H also has order n. Okay. Now what we see is this, that is if G1 is isomorphic to G2, then many properties of the elements and the subsets and the subgroup structures are preserved. So what this idea of isomorphism will do is that it shall help us classify the groups or same types of groups. So let's go over that gradually. So for instance, we know that if we take z plus, right, or set of integers with respect to the addition, then this is a cyclic group generated by 1 or -1, right? Now, and in general, if say you have a cyclic group, okay, or let this be a cyclic group, that means what? That this cyclic group is generated by A, or we shall do this. Let this be an infinite cyclic group. Okay, so that means the order of A is infinite. And remember this, when we took cyclic groups, that this was simply A to the power K, right? A to the power K, where K belongs to Z. And right here you can see that we are getting a lot of similarity visible already. So in other words, let's just go ahead and show that any infinite group, any infinite cyclic group is isomorphic to this, the additive group of integers. Okay, so what we are going to do is that I think this would be any enough. Okay, and what I'm going to do is I think it'll be easier to write the proof if we show the mapping from from Z to that cyclic group A. So let's take our map phi, okay, from Z to A, and we shall just go just like with the flow of the looks, that is, we are defined by, or we are taking this defined by phi of an integer k, okay, equals ak. All right, and remember this, our cyclic group under consideration is infinite, right? Okay, so if I take the if I take a sum of two elements, say we take k plus l, and I'm not writing it, but we are taking k and l from Z, then this will be a to the k plus l. All right, and even though this is not the exponential map in the sense of from r to r plus, but behavior is the same. Okay, so this will look very familiar to you, right? So what happens is this shows that this equals what? Phi k times phi l, because ak is phi k and al is phi l, right? So the operations are respected, right? Now, any y, actually I'm just doing this, that is repeating earlier proofs, hope not boring you too much. So any y in this cyclic group may be written as, so remember this, all the elements are powers on A. So may be written as y equals a to the, let's say, r, okay, for some r in Z, okay. So now we have phi r equals a to the r equals y. So this shows that for any y in cyclic group, okay, we have an r in Z such that phi r is y, and that shows it is onto a surjective. All right. Now let's use or check the last property, that say we have, because we still have to show that it is 1, 1. So say we have phi r equals phi s. So what will that mean? That will mean that a to the r equals a to the s, right? Now, if we multiply by a to the negative s on both the sides, then what we shall get? A to the r minus s equals the identity. Now, remember this, that we have an infinite cyclic group. So that means what? That means a to the r minus s equal to identity means r minus s equals 0, and which gives us what? Which gives us r is equal to s, all right? Or In other words, phi is injective or phi is 1, 1. Okay, so we have this isomorphism. Now let's just show another fact. That is, let's look at the situation or the case when A is a finite cyclic group. Okay, so let A be a finite cyclic group, okay, of order n. Okay, and then in this case, what we mean is this, that n is the least positive integer such that a to the n equals how much? Identity. Okay, so here we can see that the distinct elements of A will be who? They will be E, A square, and A cube. Okay, A square, A cube, and so forth, so on and so forth up to A to the n minus 1, because A to the n becomes identity again, and then the cycle repeats. So here, as it might be becoming apparent from the symbol, that we have this cyclic group is isomorphic to the additive group of integers modulo n. Okay, so and the map should be quite apparent. That is, if we did this, say we took phi of a to the r, okay, and so phi of a to the r, Zn can be thought to have elements 0, 1, 2, up to n minus 1 when we reduce everything by modulo n. Okay, so but still let's just write it as r mod n. Okay, because when we multiply two elements here, if the power exceeds n, then we can always reduce it down. So again, for just as before, if we took the product of two elements on the left and here, okay, well, I just happened to go from this time I put the integers modulo m on the right hand side. All right, but it just seems to work out fine. And again, you know that inverse of an isomorphism is again an isomorphism. Okay, so what this will be, again, by the rule for powers, this is a to the r plus s, and what this would be r plus s mod n, sorry, and by the property of modular numbers, okay, we have that this is simply r mod n plus s mod n, right? So this is a homomorphism, right? Now this is onto because take any number in Zn, take any value in Zn, it can be reduced modulo n to one of these powers, okay? So for any, let's say, x bar in Zn, all right, where we are doing this, so x bar in Zn, and by doing the modular arithmetic, okay, we can do this, okay, with 0 less than or equal to, and again, our division algorithm, would guarantee that we can bring it in this range, right? What happens is a to the power x, or phi of a to the power x, is going to be simply x bar, right? Okay, x equals x bar, and I think we should stop distinguishing between them at this time. And now for the 1 1 portion, so this shows you that the mapping is onto, because what you could do is take any element in here, then there is a pre-image in here. Now for the 1 1, what we have to do is let's let a to the, let's take r and s. Phi of a to the r equals phi of a to the s, all right? And these would be what? R mod n, okay, equals s mod n, and what that will give us, that the two elements are the same in that set of, in the set Zn, right? Okay, so R and S. I think we just went to formal or routine, but that's okay to see it this way. All right, so this is on. So all that, I mean, what we just saw was this. I mean, if this was a routine proof, and I'm not going to write such a routine proof in the rest of the presentation. Okay, so what we just saw was that all the cyclic groups, okay, can be viewed as Z and as Z or Z modulo n for some positive number n, okay, for many purposes, okay, for most purposes. And we will just go ahead and narrow this down further in the future presentations. Okay, now let's take another example or another idea. Now I brought this example back from our presentation 5, and there we saw that this is a group with respect to matrix multiplication. Identity is this, you have seen by now, and here you can see a square and b square and c square. They are all equal to identity E, and this is the multiplication table, or you also call it Cayley table. Now, by the way, this group is called Klein 4 group. Okay, this is called Klein 4 group. Okay, and then we also had done like Hamiltonians, right, in which we had -1 1, and actually let me just write it like this. This we took, you know, quite a few times. Okay, and here you had I square, j square, and k square, all -1, and I times j was k, ji was -k, etc. Now let's just go to Sage Math. We haven't visited Sage Math, and see how these groups show up in there, and then move on to our next theorem of this chapter. So this is Sage, and it has Klein 4 group stored in it. All right, and we will go over this later, how to put those in, or our own groups in later. Okay, so say, and this is how we can recall it. Okay, all right, so this is this, and if we ask it to list the elements of K, you can see that the elements are listed as permutations, right? Likewise, if I take H to be quaternion group. I hope I didn't make any spelling mistake. Okay, all right, and ask it to list H. Okay, you can see that H has 8 elements, and what it does is it gives us a list of 8 permutations. Okay, so what and if you played with Sage Math, I mean, we have not been able to do much with this, okay? But if you played with this, for own curiosity, you might see permutation groups. So far, in what we have done, are easiest to handle by, if we are looking at the groups that are stored in there already for us, okay? So what we are going towards is, or what our next theorem says is this. Actually, it's not our next theorem. Our means not mine, of course. So the theorem that I'm talking about is called the Cayley's theorem. Okay, and it says that every group is isomorphic to a group of permutations. That's how you saw that Sage Math just gave us those two groups, the Hamiltonian and Klein, as group of permutations, even though we had not looked at them that way. Okay, so I'm not going to prove it, but the book does a good job of proving it, and uh, so the way we do it is this, that let's have G as a group. So let's let G be a group, okay? And remember this, what were permutations when we defined them? They were bijective maps between a set onto itself, and here the set is G. So for any element little g in G, okay, we can take, okay, a map which you can see very easily, that is a bijection, okay, from G to G, and you can define it by that fgx is gx, okay. So what we are doing is we are multiplying every element in G by this little g on the left, okay. This is also called, so, and then what we would do is this, okay, or you can, the book proves that this is a group for G belonging to G, all right. Okay. So this is a group, and of course it is a permutation group, okay. You can call it, sorry, permutation group, okay. And I mean a permutation group rather, okay. Now if you take the correspondence that G is assigned to F sub G, okay, then what happens is that correspondence will be an isomorphism. Actually, it is also called left regular representation of the group G. Okay, there are other ways of, showing such a correspondence. So let's see this here, that say we have a group and we want to create a permutation group that is isomorphic to that given group, how we would do that. All right. So let's just begin with our clients for group. All right. And see how did Sage return the output that it gave us. So let's come to our group, and let me just erase this portion here. Okay. And we would also erase this top portion, because remember this, once we wrote those symbols for the matrices, okay, then we had the elements of our group as E, A, B, C, just like that, right? Okay, so we got this, and let me move this up, okay? So here we go. All right, so our group G is, that consists of A, E, A, B, C. So what happens according to that left multiplication? If we look at EABC, that goes to EABC, just this portion right here, okay? And then say we want to look at the image of A, then A goes to, again, we have EABC, and what we got here, we will just get these elements. So what we get, AECB, right? Okay. Now when we look at the image of B, okay, so here B will go to EABC, all right, and then we have, when we multiply by B on the left, that's what we are going to get. And now let's look at the images of C. So for C, what we will do is we will choose the this row in which we multiplied everything on the left by C. So we got C, B, A, E. And we can again write it as, if we want, uh, as 1, 2, 3, 4. Now here we shall take a choice, then stick with this. So we got 1, 2, 3, 4, and then we have 1, 2, 3, 4. Here we got 1, 2, 3, 4, and then we got 2, 1, 4, 3. Here we got 1, 2, 3, 4, and then we got 2, 3. Excuse me. 2, 3. No, I made a mistake, not we made a mistake. Okay. Actually, this should not have been 2, right? 2 is for 1. So here B is 3, C is 4. Then we got 1 and 2. And here we have 1, 2, 3, 4. C is 4, B is 3, A is 2, and E is 1. Okay, so we got these 4 elements, and remember this, what Sage does is it writes this as identity, or it writes identity just as do nothing. And if we look at this, then how we can write it? See this here, we can write it as cycles 1, 2, 2, 1. So that becomes one cycle. And then 3, 4, 4, 3. So we did this, we wrote it as a product of disjoint cycles, right? And if we bring this in here, okay, then what we got, 1 goes to 3, 3 goes to 1. So we will write that as cycle 1, 3, and then the cycle 2, 4, right? And then when we go to the last one, no, or rather this one, okay, what we got here is 1 goes to 4, 4 goes to 1, so we got 1, 4, right? Then 2 goes to 3, and 3 goes to 2. So we have these 4 permutations, and let's quickly see what Sage gave us. So what we see is that our list is right here, right? And so in this, if you see, only 1, 2, 3, 4, that one matches with an output there in the client's 4 group, and these two look different. Okay, but still this is a subgroup. So let's see if this subgroup here is isomorphic to what this listed as client's 4 group, or rather client 4 group. So you can see both of them are subgroups of the symmetric group on 4 symbols. So let's do this. Let's take symmetric group 4. Just define that as our big groups, and then we are just going to take our elements that we got here, okay, defined into this. So let me just type it, okay, because many of you are new to Sage, and I made a mistake myself. I had to write that this guy A is in S4. Okay, so A is in S4. That is, I just defined this element. So we got this. Then B is in S4. Okay, who is B? 1, 3. Okay, 2, 4. All right, and then we close parentheses. Then we have C. So again, we didn't have to take all of them, but I just took it. Sorry, 4. Okay, all right. So we got all these elements here. Okay, so now what we will do is this. Let's just go ahead and define a subgroup H, okay, of S4. And what this will be, let's take it as the smallest subgroup that contains A, B, and C. Okay, so we have A comma B comma C. Okay, and so if we do that, then H is a subgroup, and if we list H, okay, it will just give us the group that we had. And as I told you that we don't really have to have say for instance, if we say H subgroup, and this time I only take 2 of these, okay, all right, then this is the subgroup subgroup L, okay, and in case I look at this list L, I get the same subset, okay, or sorry, same subgroup, okay. Now let's ask this, or let's check this and this, they are looking different, but they should be isomorphic, right? Because we just defined them in the same style. So we can do this, like if we look at K, if we look at H, then this element, we can make it correspond to this, and these guys can go to either of those two, or we may just ask this, that H, so we are asking this Sage Math a question, that is this isomorphic, sorry, morphic to, okay, K. So that's how, that is, we are asking, is our subgroup H, the subgroup that we got, is that isomorphic to this subgroup that Sage gave us? And it says, yes, it is true. So what we find is this, that we found this as the transformation group if we went in the style of the Cayley's theorem, and this is what Sage gave us, but no problem, these two are isomorphic. Okay, so let's just go ahead and construct another one. Okay, now let's take this additive group of integers modulo 4. And instead of this, I can write it like this, because 4 is going to act like 0. And here we removed the bars, okay? And now we are doing informally isomorphisms. That is, we have these elements and we got modulo 4, and we are going to create permutation groups on 4 symbols. using the left multiplication. So now we are going to look at this, that where each of the elements go. So here we are going to add 1, so we get 2, 3, 4, 1. Here we are going to add 2, so what do we get? 2, and then 2 plus 2 is going to be actually 4, and 2 plus 3 is going to be 1, and so 2 plus 1, I'm making mistakes now. This is 4, then 2 plus 3 is 1, and 2 plus 4 is 2, right? And 3 plus 1 is 4. 3 plus 2 modulo 4, of course, is 1. 3 plus 3 modulo 4 is 2, and 3 plus 4 modulo 4 is 3, right? And here you can see we will get the same thing because 4 actually is 0, right? So what do we get here? Here we simply get the I think we just get the cycle 1, 2, 3, 4, right? So 1, 2, 3, 4, that's the cycle we got. And here, if we write the disjoint cycles, okay, then what we shall have is that 1 goes to 3, 3 goes to 1, so we'll get 1, 3, okay, and then 2 goes to 4, 4 goes to 2, we get 2, 4, and then for the very last one, what we get is that, not the very last one, sorry, I went ahead too fast. I mean, still we are okay that we got the identity element. Now for the next one, what we have this, and this is going to be, we'll just bring that back, okay. This is going to be 1 goes to 4, 4 goes to 3, right? 3 goes to 2, and 2 goes to 1. So this one acts like this. I mean, or yes, in cycle in this manner. So the 4 elements that we have are, which are the 4 elements that we got for S4 as the subgroup isomorphic to Z4, we got this. First we got a 4 cycle, and then we got, so something is wrong here, let's check. 1 goes to 4, and 4 goes to 3, right? Okay, so I should write 3 here, okay? Then 3 goes to 2, and 2 goes to 1, okay? Just rushing too much for no reason. Okay, so here, so these are the 4 elements. Now let's just go ahead and see if this is a subgroup. We can just, there are only 4 elements. We can check very quickly whether that is closed. But let's just go ahead and get used to our Sage Math. So what we will do is this, that we should go ahead and then just take elements. Say we will take, since A, B, C are exhausted, so we will just take U, an element in S4. Okay, and that was easy. We had 1, 2, 3, 4. Okay, so this is one element here in S4, and then, so let's take V as, sorry, this element of S4. Which elements we had in there? We had 1, 3 times 2, 4, okay, and so we got this as V, and let's take an element W, the very last one. Okay, so that was a cycle. 1, 4, 3, 2, right? That was okay. So we got this. All right. Now we will take, so we have taken like K and H and L as those symbols. So let me just take another symbol. Let's just take P. So P, we want P to be the smallest subgroup that contains these elements. Okay. So subgroup U V W, and we are just going the lazy way. Okay, so we got that. Okay, and let's just if we list P, we know we will just get these elements with the identity combined, and that's what exactly what happened. Okay, now we want to know whether this P is a subgroup of S4 or not. I mean, we could check the closure, but for the bigger bigger subgroups, okay, this will be quite handy. So we get I mean, P is that a subgroup of S4? So let's check. Okay, all right, I made a mistake somewhere. And the mistake is right here because I was, we have capital S4 and I wrote a small s4. So let's just go ahead and fix it. Okay, I told you I'm not good at programming. Okay, all right, so it says true. Yes, that is true. Now let's check another thing. Remember this P, which is isomorphic to Z4, is a cyclic group. Okay, and K, the client's group, that is not cyclic because remember, all ABC, each one of them has order 2. All right, so that cannot be isomorphic to this group P. Okay, so let's see. So let's just check, using Sage, that whether it shows that if we give it K, all right, the client 4 group, and we give it Z4, which we came up as P, whether they are isomorphic. And how do we check isomorphism? We'll just write one of the sets and then just ask if it's isomorphic to the other one. So I'm just doing this. K is isomorphic, okay? And here we have P, the other set. Let's ask. It says false. And of course, we expected it because this is cyclic and this is not. And that property is preserved under isomorphism. Okay. So we now saw that that we can have a correspondence called isomorphism between two groups, and many major properties they are preserved in there. So when you go ahead and do more exercises, you will learn more. And very importantly, we learned that every group is isomorphic to a symmetric group. All right. So we shall take up further, start with direct product from the next presentation.